Okay. So, how are you doing today? All good? Okay. So, what were we talking about last time? Priority queue. Very good. So we're going to just do a quick recap for you guys. What did we conclude at the end? We said we had the ADT of priority queue, and we wanted to implement this ADT. We're going to use what we tried the sequence. We tried the sequence, and we also tried, technically we tried sequence, but we tried two versions of the sequence, which is what? Ordered and unordered. True? Very good. What did we conclude if I'm trying to implement the priority queue with unsorted sequence? We had a problem with removing the minimum. Why? Who can remind me? Riley.
The minimum in unsorted sequence.
Very good. Let's go a bit to the basics. What do you mean by remove min in priority queue? What is the remove min? Yes. Exactly. So we're going to, because it's a priority queue, we need to remove the one with the highest priority. Why is minimum the highest priority, not maximum? Yes.
So queue is first in, first out. Basically, the highest is gonna be first. So when we move in, it's gonna be first.
Which one is first in, first out?
Highest is queue, right?
But this is priority queue. We said in a priority queue, we have to remove the highest priority. Doesn't mean it if it came first. Let's get all on the same page before we move, because if we don't know these basics, we're going to struggle. Yes. Why? So why is the lowest number? Why is the minimum key is the highest priority? Who decided this? Zach.
Because that's how we decided to define it.
Very good, guys. Always go back to the basics. I want you to understand what you're doing. You'll go to another company, they are using maximum as the highest priority, not minimum. They decided to implement the max key as the highest priority. Here, we're following the book and the standard. So usually the min key is maybe the highest priority. So I want to remove the minimum. I want to find who from these elements has the highest priority, because it's going to be labeled with the lowest key number. So I do remove min, I'm actually getting the highest priorities. That's the whole idea of a priority queue. Not comparing to the normal queue where no, it doesn't matter if you have a heart attack or a headache, first in, first out. Okay? And then Riley said here, the remove min is going to cost me O of n. Why? Because it's unordered sequence. So I build this priority queue with a sequence, let's say an array, for example, that doesn't have ordered min key. So I have to search which one has a min key. So if I want to search in a linear data structure, it's going to be O of n. And then we said this thing for the remove min, if I have a sorted array, I can just now get the index 0 all the time. Why? Because it's sorted for me. So in a sorted array, what do we have? I always have the minimum key here, for example. That's the highest priority, and then 5, and then 10. So I can O of 1 to remove. But what is the problem with the sorted array? The insert part. Because I want to insert the minimum key. For example, I want to insert 1. I have to shift all of them. So another thing that we observed about the priority queue, if I want to use the priority queue to sort my elements as a sorting. And we said we can do that by implementing, for example, sort and insertion. Now, selection sort represent what? The logic of selection sort represent an ordered sequence or unordered sequence? the selection sort. Think about it. We're searching and selecting the minimum. That means unsorted, right? So O of n squared is going to take, and then we said the insertion sort also is going to take O of n squared. But why are these sorting? That's the link that I want you to base. So let's say I'm using a priority queue to sort things. Why are we ending up with O of n squared? We said we're ending up like this because the data structure that we're using is linear. So we're ending up with O of n squared. Now, someone came to me after the class and said, but there is a better way. Why we're using sequence? Actually, we're using sequence to show you that there is a better way, just for you to be able to compare. Okay, so again, people with PhDs in math, computer scientists, said, you know what? We can actually, this is not enough for us. This is not enough. We can have a priority queue implemented, but better than linear. Now, from the bag of data structures that we have, which data structure we talked about and implemented that you can use to have something better than O of n? Yes. Trees. Who can remind me why a binary tree is good and it's better? Yes.
Because in like a balanced binary tree, every single time you go one node down, you're eliminating half the data.
That's good, but we didn't explain this yet. That's binary search tree, but that's good. So technically, because if it's balanced, what would be the maximum height, James? Log of n. And we actually proved this last time, correct? So if I'm using a linear like this, the maximum, my worst case will always be O of n because I have to always go linear one by one. We said the logic behind a binary tree is we can jump. We can access things in a faster way. And then it's going to be what? If I have a tree like this, the maximum is this, like this. So vertically, not horizontally. Okay, that's good. Now, do we all agree that it is log O of log n because the binary tree height is always log of n? Do we all agree on this? Any objection? It's now or never. Any objection? James?
Yeah, it's almost never going to be a log of n exactly, since it's not going to be a perfect tree. However, you might have a complete tree, so it might be log of n plus 1.
Very good. So binary tree, no, we don't have the guarantee that it's O of log n. That's why we're going to use here. We hope to have a perfect tree, but as James said, we cannot have a perfect tree. That's why we're going to use a complete binary tree. A complete binary tree is O of log n. Not just a normal binary tree. Okay, because in a normal binary tree, you don't have enough information on the levels of which one is filled, which one is not filled. So you don't actually, you're not able to predict exactly the number of elements inside the thing. Yes.
Why exactly do we care so much about O of log n versus O of log n plus 1?
No, we don't. I'm saying with the perfect and the complete are good. Both of them are going to end up with O, but we're saying if it's just a binary tree,
Okay, yeah.
not the case. That's what we're saying. With the perfect, no, it's also going to be log of n. But we're saying, okay, it's never, almost never going to be perfect binary tree. So very good. We did all of this introduction. Why, guys? Because we want to say that we're going to use a better data structure to have priority queue implemented. And then if I have a better data structure to implement the priority queue, and I then use this priority queue to sort, what will happen? I'll have a better efficiency even when sorting. Okay, guys, so that's the logic that we're going to follow. Now, there's something called Heaps. Heaps uses complete binary tree. Again, why we're choosing complete binary tree? Because we're able to predict a bit. When you hear the word complete binary tree, you know for sure that what? H minus 1 is always perfect, and then it's left filled. So you're able to navigate, and you're able to predict at least the H minus 1, how many elements do I have? Now, one thing I want you to keep in mind, I don't like dummy nodes. It's confusing, I know, but we need to put them sometimes in the book. They are using them. So in case you see these things, you don't get confused. What you care about, guys, is that that's what you care about. This is the one that's going to be what perfect. And then this is the one that's, but let's say we're using dummy nodes. Instead of this being the H now, this is the H and this is H minus 1. But don't get confused about that. Doesn't matter. It's going to still be O of log n, just for you to have to see both dummy nodes and not dummy nodes. Now, heaps are two types, min heap and max heap. What is a min heap? It means on the root, I have the minimum key. Max heap, that means on the root, I have the max number. Why is this important for me? Riley.
Highest priority, so
Let's say I'm using min heap and my highest priority is the minimum number. Why it's important for me to always keep it on the root?
your personal look at it.
Which means from an algorithm analysis perspective, it means what? Exactly. My problem with the unordered, for example, was if I want to remove min, I have to go and search for the min. So I have to search for the min, it's going to take me O of n. Then we said, you know what, we can use ordered, and it's always going to be the first index, O of 1. But we had a problem inserting things inside the order. So the heap will solve both cases. It will have at the first index on the root, always the min key, but it doesn't have to be ordered. Do you see? These are not ordered. So that's the concept of heaps. You're solving both problems introducing this. So for now, the definition of min heap is that always the key of the parent is less or equal than the key of the child. That means always the parent is less than the child, the parent less than the child. It doesn't have to be the left one less than the right one. Don't get confused. That's why I told your friend here, we're going to explain something called binary search tree later on, where you have to have these ordered. Now, for heaps, only the parent and the children relationship is important. You don't care about your siblings. Okay? Now, the max heap will be what? The opposite. The root is going to have the maximum number. That means the key of the parent is going to always be greater or equal than the key of the child. Very good. Again, as we said, we don't need to add dummy leaves or dummy nodes, but we're going to see an example with them. Do I need to explain this? I'm not going to explain, even if I need to. You'll have to go and watch the lecture that I published. We talked about this, we explained it, and also it is in the recorded video. If you want to remember, how did we conclude that the height of a complete binary tree is log of n, please, you can rewatch the lecture. From now on, everything we're using, heaps, binary search tree, AVL tree, I need you to know for sure that the height is always log of n. The math background of it, it's your responsibility to rewatch the video. I don't want to re-explain it every single time, but we know for sure that it is log of n. Why this is important for us? Because if the maximum that I need to go, again, here we're going vertically, the maximum, the worst case is I want to reach this one. And if the height is log of n, that means it's going to take me log of n time to reach there. Is this clear? Very good.
Yeah.
Now, someone will tell me what? Here you're giving all examples with just numbers, but this is a priority queue. That means it has a key and also it has an element. For sure, but for us to not draw the trees like this, each time we're going to only draw the key. But of course, each key has an element because this key is just the priority of this element inserted here. Now, for example, if you're using Python, when you're building this, Python supports what? Tuples. C++ support pairs. In Java, there's no direct support for this. That's why we use we have to create like a node thing and then sequence on all these things. two rules that I want you to always, guys, remember. Super important. That's usually many people make these mistakes in the midterms and the finals. Is whenever we do a remove min, we're going to remove the root. That's very good. What will happen if we remove the root? Yeah. You cannot keep it empty, yes?
Even in the case of the max, but even if.
Yes, yes, always. So in the max, it'll be remove max, not remove min. Okay? So if I'm removing the root, I'll have to do something else, which is rearrange the heap. Because the concept here is heap. It's a concept of a heap. We're going to understand what is the concept of the heap. I have to always keep it a heap to continue. So I removed the min. O of 1, O of constant. Riley said I need to replace it with another number. The best thing to do is another O of constant, which is replacing the last element with the root all the time. We're just going. The second step will be replacing the root with the last element. So now I have this. I replaced it, and I'm good to go. No. Riley's saying no. Who can say why no? Melanie. Very good. You see? I don't have to explain anything today. Logic. Basic logic stuff, guys. This is not a min heap anymore. I need to keep the idea of a min heap. What is the idea of a min heap? The minimum needs to be in the root. So what should I do the next? What is the next step here? Taha. Swap. But what should I swap? 5 or 6? 5, of course, because it's a min heap. So from an algorithmic logic, how is the program deciding which one to go left or right? You're going to have an if condition for sure. And you want to compare this by this. Now someone is going to come and yes, someone will going to, I don't like to stand. Someone is going to come and tell me, but this is, let's say I'm doing this with an array based. So if I want to compare the second or the third, or like the children, I have to traverse. Who wants to reply to this? Do I need to actually traverse to compare my left and right? Fida? Very good. Do you remember when we said, even if you're implementing this with an array, not a linked list, what are the rules? We said this is going to be I, 2 times I, 2 times I plus 1. That's how it's going to always be. Okay, guys? So you have to, the machine can do the calculation. So primitive operation of 1 all the time. So I'm going to compare the index. So let's say this array is called A. So I'm going to compare, is A index to I less, for example, than the array of 2I plus 1, the index, and then we're going to make this decision. Okay, so don't get confused. Even with a array-based implementation, it's not going to take me more than O of 1. Very good. Now, the operation of replacing, it's called down heap. The idea of down heap is when I'm always comparing the top with the children, with the parents. Okay, guys, so I need to do a down heap. So this is another example here. Who wants to do this example with me? So we removed 3, and I'm telling you we're going to continue and do the 20. What's going to happen after this? I have a 20 at the root now. Is this a min heap? That's the first question you're going to ask yourself. It's not a min heap anymore. What do I need to do? Down heap. Okay. Who wants to do the down heap? Let's see more. Ralph. No, you don't go with the code, just the logic. So what's going to happen? We're going to compare with what? 4 and 6. So the 20 is going to go where?
Either 6, but it's going to be the 4.
4, of course. So I'm going to have here now. So I had the 20 here. Now the 20, I'll have 4 here and then 20 here. Recess? Or should we continue? Okay, continue.
Now we have a 4 and we go here and we take it out. We're gonna put 25 on top.
No, we're not going. Okay, very good. Thank you, Ralph. I'll come back to you. Curly.
21.
Very good. This is also another mistake. The down heap, it's not even a mistake. I didn't even explain it yet. So it's not a mistake as a mistake, but I mean, the down heap is a full operation to remake the heap as a min heap again. So when I did this, I brought the 20 here. The first down heap operation it didn't end yet. I have to make this a min heap. This is not a min heap. The root has the minimum, but what did we say in the min heap? The parent, he has always to be less or equal than the child. Is 10, is 20 less than 10? No. So as Curly said, we're going to continue. Very good. So here, I'm going to take this, I'll have 10, and then I'll have 20 here. Who wants to continue? You had your hand raised.
I
Do well.
to change it with.
What options do you have? Like, think out loud so everyone can think with you.
The naked is 13 and 19.
13 and 19. So you have two options. It's either replacing with 13 or 19. What should you do?
In both cases, they would work. Because 19 is, both numbers are.
Yeah, but think about it more. Let's say I replace it with 19. Okay, guys, I replace it with 19 and then I have 20 here. Is this a min heap? No, I have to check again. Okay, I'm going to replace it again with 13 and then 19. So I did two operations instead of right away do one. So technically, what will happen here is that we're going to first check which one is the minimum between the children and then replace it with it right away. So here I have 20 here. 13 is the minimum between these three. I'm going to right away have 13 here and then 20 here. And then this is the last one. I don't have to change it. I'm done from down heap. Is this a min heap? Very good. I can move on now. Yes.
Why, if you replace it with 19, it's not a min heap?
You replaced it with 19? Okay, let's see it. Very good. So let's see here.
Yeah, it was smaller, but it's just compare.
I have 20 here. I replaced it with 19. And now the 20 is here. Correct? Okay. This is the rule of the min heap. The parent, he need to always be less or equal than the child. This is the parent, this is the child. These two are the children, 13 and 20. Does this apply? Is 19 less than 13? You see what I mean, guys? So step by step. Then with practice, you're going to, it will click very quickly. Yes, right.
If you put 20 at the top just because we're left field, right? That's the reason so that it doesn't.
Exactly. Do you see now why we chose the idea of complete binary tree? It's left filled, so I know for sure that the last one is going to be the last one. Okay, and there is an order. So yes, Joel.
Then just to confirm, you would pick the smallest number between the two children and then swap it right away.
Yes, all the time.
Sense?
Yes, always. So if we continue here, you will see this, that, okay, I have 20 here. Which one is the less, 4 or 6? 4. So I go here. Which one is less, 21 or 10? 10. So I'm going to replace it with 10. Correct? So that's, I replaced it with 10. Now 20, 13 or 19, 13 is less. So I'm going to replace it with 13. Now this is a min heap. Yes, Anthony.
Yes, for the implementation of this algorithm, do we always choose like the last node that we added to the tree in order to do this process of going from the root?
You replace it with the last element in the array.
To find that last element, do we always keep a pointer it, or do we just do a to get it?
No, technically it's of one, because whenever we have an array, you're going to always have access to the first one and the last one, because typically we're always keeping track.
And we decided that's always going to be.
Why do we always keep track? Do you remember, if you look at all the algorithms that we used, what do we update all the time? The size. Whenever you answer something, so if you have the size, what is the index? The size. So you're going to go there. And if you remove something, you're going to say size -1. So you always have index 0 or index 1, and you'll have what? The index of the size. So you always have them. So it's O of 1. We didn't even reach log of n yet, guys. So be careful. Now, we're just proving that each operation is O of 1. But we know that removing the min is O of 1, and then replacing the last one with the root is also O of 1. But what about the down heap, all these steps? That's what we're going to use the log of n, because this down heap, we went from where? From here, look, till the last one, till h. And this is my worst case. That means my worst case is going to be, it will take me h, which is log of n. Okay, but in a normal array, in a sequence, my worst case will be the last element in the array because it's linear. I have to go linear, step by step. Yes. The complete binary tree question. Yeah, so why do we always need it to be filled from left to right? Because it will make it much easier on the program that you're going to write. Because you know for sure that if you're replacing, for example, with the 25, you know that all of these before the 25 are filled. So it's easier when you're going to write the math equations and everything. For example, the 2i, everything's going to be much easier when you have left filled. That's the whole idea. If you have gaps inside your array, it's not going to work, because these, by the way, what do we mean by left filled? That means we have an array implementation that doesn't have gaps. That's the whole idea. If I have gaps, it's going to take me more time. So in this case here, guys, this is going to be h-1 because of the dummy leaves. Don't worry about it. At the end of the day, it's going to be O of log n. Dummy or without dummy, because h-1 or h, the same thing. Now insertion. We solved the remove min, but we want to insert inside this priority queue. New patient or whatever came to this, I want to insert here. I'm going to always insert from the last element. Why? Because I know that I have space there all the time. I don't have to move anything. So I'm going to insert here. Is this a min heap? No. So what do I need to do? Down heap. I need to go underground. No, up heap. So that's the idea. That's the key. If I'm inserting something from the root and going down heap. If I'm removing something, I do down heap. If I'm starting from the bottom, I'm doing up heap. So very good. Yes.
How to do up heap? Because in this case, if you, because you need down heap is when you have no.
Yeah. Yes. Down heap and up heap, we always do it because we want to rearrange. We want to rearrange the heap. So if I insert, because I'm inserting from down, from bottom, I need to go up. In this case, I don't have a choice here, so I'm going to replace it right away with the 6. 1 is going to be here. 6 is going to be here. Is this a min heap? No. So I need to continue. Again, 1 is going to be here, and 2 is going to be here. This is a min heap. I'm done from the up heap process. So let's take another example. So I want to insert 6. Who wants to do it? Let's take from this side. Yes.
You insert side 25.
Okay. So it's what? It's a complete binary tree. Do you see why it's so easy to use a complete binary tree? I know where should I put it. So where I should put it here. So that's my 6. Very good. You want to do the next step.
Yeah, and you would swap it with the 20.
Why? I want you to give me the steps that you're thinking about so everyone can benefit. Why? And the midterm,
You
know
take the
that-
child and compare it with the parent, and
very good.
if it's smaller, or yeah, if it's smaller than the parent, you would swap them.
Very good. So now we're comparing the two keys. I have 20, I have 6. Very good. So let's take someone else. Thank you so much. Luke.
6 is 7.
Because 6 is smaller than 7. Okay, what should I do now? Yes. Stop. Very good. This is a min heap. I don't have to continue anymore. Correct? I checked everything. Very good. and then I stopped here. So that's the end. Yes, look.
One question, when I inserted 6, it was already a min heap, so
No, so look at it. You inserted this. Why is this a min heap?
it's 3.
The root.
already.
No, again, always remember, guys, having the minimum in the root doesn't mean it's a min heap. Min heap means all the parent parent. Papa and maman. So all the parents has to be less than the children. Okay? Now, James.
I just want to make sure, so the idea is that instead of focusing on the indexes on the fields to the left or right, it's more focused on data balance and the parent is always under a certain relation.
So we're not focusing on being balanced because for us, it's already complete binary tree. So we know that it's complete binary tree. We want to focus on always having the parent key less than the children key. Or if in the max heap, we want the parent key to be greater than the children key. Depends on the type of the heap.
How do we determine where's the node place, the new node place? I know which parent it goes to.
Yeah, so always, if you look at this, let's say I inserted 6 here, right? I just have to compare it with its parent. Is it less or so? I only compare it. How can I do that within real implementation? Because we know that we know the indexes. Okay, so that's it. Yeah.
Sure. So, why is it placed on 20 instead of 8? Is it
Because technically, look, very good question. Look at this. Is 6 connected to 8? It's not. We said in a binary tree, the parent is what has left and right. That's the only thing. So you can move, 20 can only move like this or like this, and 6 can move either like this or like this or like this. 8 it's not connected with 6. Why would I go to 6? I shouldn't. Because if I have to go to 6, then I need to traverse. It's going to cost me more time. But if I'm just swapping, do you remember if you go back to the last section, last lecture, the operation swap, it's O of 1. That's why I want to only swap, not like traverse or something. Because I want to keep each operation O of 1.
Okay.
Okay.
So that way, so left and right, just make sure how it goes from left to right. It's is that just how we're doing it in, or is that how else?
If you're asking about the implementation, you're going to go left and right based on the indexes of the array, because we said each index I, the left of this I is going to be 2 times I, and the right is going to be 2 times I plus 1. So I'm going to compare them. I'm going to check, is the index in the array of 2 times I less than the index of the array? And then we'll see, and then we'll swap. So it's going to be, when we go to the implementation in the array, you're going to understand it better. Okay, very good. So that's our conclusion here, guys, is that we were right. Yes, we tried implementing this with a sequence, which the sequence is what? Is just a representation of a linear data structure. And we had for insert O of 1, n, 1, 1. So I'm always having O of n. But here, in this case, to insert is O of log n, to remove is O of log n. But why it's not O of 1 when I'm removing? Because I'm removing from the root. Exactly, because I don't count, my cost is not just removing from the root. It's removing from the root and then rearrange the heap. That's my actual cost. So I'll have O of log n, O of log n, O of 1. Which one is better? Of course, the logarithmic is better. So that's why whenever you want to implement anything related to priority queue ADT, the idea of having something in priority, you'll find online everyone uses a heap. They don't use sequence. Unless, now let's talk a bit of, just outside of the box, not related to this. When would you, when would you use the priority queue with sorted sequence instead of the heap? In which case? See more people. Think about it a bit. Again, think about it from the way that we did the scenario yesterday, last time with Zach and Aaron. Why would you even choose something? Because of what? Because like depending on what you're going to choose, which one is better? Before that, yes. So circumstance, but what word do we use? We don't use circumstance. What do we use as a word? Yeah, problem. Depend on your problem. Okay, guys. So if my problem, let's say I'm giving you, I'm a client and I'm telling you, you know what? I have something that it's fixed. I don't want to insert anything to it. It's impossible. There is no even interface to insert. I can only remove. So now, if I want to only remove, it's going to always take me O of 1. But here, it's going to take O of log n. Then I'll choose this. Now you're going to think, who would implement something like this? You never know. Maybe in NASA, they are going to Mars. They have this very specific thing they want to. That's how it happens. The idea here is to always look at the problem, and then that's how you're going to choose. But if you don't know the exact problem, and you're talking about an overall efficiency, of course, heap is better. Now that's the problem here. This slide is our main problem. Because we said, okay, we solved the problem of inserting. We solved the problem of what? Of removing. What about creating the heap? Because how do I create an array? How do I create a sequence? If I have n elements, how much time is going to take me to create the array? Of n. Why? I have n elements, so it's going to be one. Each time I'm just doing 1, 1, 1, n times. But now, each insert is O of log n for me. Each insert I'm doing is O of log n. So it's going to take me what? Exactly. N log n is going to be log n times. So that's not very useful. Because to create the heap, it's going to cost me a lot. But then again, they had a meeting, computer scientists, mathematician, they had a meeting, said, you know what, no, we're going to find a solution. This solution is going to be, of course, everything is math based. So we're going to see how they came up with the idea of constructing a heap, but staying with the O of n. Okay? Something called bottom-up heap construction. So what is the idea here? Bottom-up heap construction is that I'm going to treat 3 nodes, each small subtree, let's call it, for example, each subtree as a heap, as a separate heap. And I fix it, and then I go. I continue. So for example, I will fix this first. Let's say I'm looking for a min heap. I'll fix this first, then I'll fix this second, and then, and I'll go there. Someone was going to tell me, okay, that means we're creating more heaps now. No. Because heap is what? It's an ADT. Heap is a concept. That because this, look, think about this thing here is just an array. So I already have the array here. I'm just thinking about a way how to move inside this array. So I'm saying instead of taking this whole array, for example, and treating it right away as a heap, which will take me to insert in it and blah, 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 let's just take chunks of this array and fix them, and then it's going to work, actually. So let's see how it's going to work. So let's say I have this one here. Again, if I want to put this in an array, if I want to represent this as an array, what is the representation? Who can tell me? Do you want to try? If I want to represent this in an array, what will be an index 0?
Be I.
Which is 2 here. And then 4, 5, 7, 3, 10, 8, 1, 9, and then 6. So this already looks like this. This is an array. It's inside the array, for example. It's like this, let's say. And then the way it moves, the way we do the remove and stuff, that's the heap concept. So here we're saying The idea of bottom-up heap construction is check this one, the last one. Why I choose this? Because that's the last one. It's complete binary tree. And I'm doing a max heap in this case. Is this a max heap, the 3 and 6? Is it a max heap? No. How can I fix it? I'm going to put the 6 and the 3. Is this now a max heap? Yes. I'm going to move. Which one is going to be my next step that I'm going to go and fix? Ralph. 719. Why? Because it's left filled. That means if I'm going backward, I'm going to go what? From right to left. So now 719, who wants to fix it and make it a max heap? This one here. Who wants to try to fix it? Max heap, yes. Just raise your hand, please. Let me see more people, new people. Yes.
Switch to 9 and 7.
We're going to switch the 9 and 7. So technically, we'll look at the 7 all the time. We look at the root. So now that's why I'm asking this, guys. I know it's simple, but I want you to know how to tackle things. If I look at the 7, it will look as if I'm doing an up heap. No, I need to look at the root because I'm going to always be doing down heap. So I'm looking at, this is my root for the subtrees. This is 7. 7 is going to be replaced by 9. Very good. So now I have the 9 here, I have the 6. What is my next step? This one, correct? Yes?
The 1 and 9 is not need to be swapped.
1 and 9? No. We read the 3 nodes. We read the small heaps from left to right. We move like this, this, and then this. But no, we don't look at the siblings. We don't look at the siblings. Again, guys, so this one's going to be easy. I'm going to do, I have the 5. Okay, who can tell me here? I'm going to ask you now. Why we're using down heap, not up heap? Because technically we're looking, we can use up heap if we want, right? Because up heap is like, for example, we look at the 8 and we go up. Yes.
Well, down heap, we will use it one time. Up heap, we use.
Very good. Do you see, guys, now you're thinking more about the time efficiency. You're thinking about algorithm analysis. Yes, it will work. If I'm looking at the 8 and I'm comparing it with 5, okay, it's going to work. I'm going to end up with what? 8 here and then 5 here. Is this a max heap? No, I have to do it again. 10 and then replace it here. So I did it twice instead of 1. If I'm doing a down heap, what's the difference with the down heap? The difference is that in the down heap, I look at the root. And in this case, this is my root because it's a small heap. And 5 only do one swap because we have to compare this first. So I know for sure that 10 is greater, so I'm going to swap it here. So very good. Yes, Ryan.
To do up heap, and sometimes when you do it later, sometimes with this one.
Yes.
You're still because it's just having a constant in front of your ends, right?
True, but why would you do this? That's the idea. Usually we don't care about constants if there is a reason for them, but like from a more like logically perspective, you don't need to add extra things for the code. So again, now what would be the next one? Is it this? No, it's going to be the whole thing now. Whenever I move to a new route that I need to, it's going to be everything under this route. So my next one is I'm looking, because I'm moving from here to this side, is everything here. Okay, so how can I make this a max heap? I need to switch what? The 9 with the 4. So I have 9 here and 4 here. Is the max heap? Okay, so the down heap process will continue till I reach 7 here and 4 here. So I'm done here, and then I'll end up with what? With this one, which is a max heap. With this bottom-up heap construction, so that's the idea of bottom-up heap construction. Now, in the example, if I ask you, construct a heap, I need to specify for you. If I tell you construct a heap without telling you use the bottom-up heap construction, you can just use the insert one, the normal insert thing. It's going to take you off n log n. Bottom-up heap construction is going to take you O of n. So you need to remember the difference between the two. This is another example, guys. Yes, Taha.
Like, I understand, the people like, why things like,
We're going to reach for this. So now we're just explaining for you how to do it if I ask you in the exam to do it, but we're going to check the math behind it. I'm not going to go through this because, yes, Curly. Yes. So what did I say?
You mentioned that in the example you asked something, so we either use the
Bottom up or the normal one?
or the insert. You said that the insert is going to be n log n.
Yes.
And that insert is log n because we inserted.
No, I meant, yeah, very good. So to clear this up, I meant how much is going to take you? What is the big O for constructing a heap using the normal insertion method? If the normal insertion method takes log n each time I insert, it's going to end up with n log n to construct the whole heap. But with the bottom-up heap construction, it's going to take me O of n. Not each insert, I mean the total cost of constructing the heap. Clear? Okay. So I'll skip this. You can check it at home, guys. But this is another example of doing the thing. So the only idea here was saying, okay, now I'm constructing this heap from scratch. Let's say my array is empty. I don't have the array yet. My array is empty. But I know the size of my array because I know the size of here. So I have this memory booked, for example. And then what I do, I always start its bottom-up heap construction. So I'm going to insert these first 2, 4, 6, 8. So the first 8 elements here. And then I'll insert the rest here. And then I'll start treating this separately. And then I'll continue doing it. So you can check it at animations. So check if you want the PowerPoint version instead of the PDF. Now, we want to know why it's O of n, correct? So we need to understand the math behind it. I'm going to go, I'll try my best to cover everything here. Before we start, you know this rule is what? The summation of 2 to the power of minus j is going to be what? Who remembers this rule? It's going to be, that's kind of like, I think, geometric series, but it's called infinite geometric series. If you reach infinite, you're going to reach 1. If you keep doing it infinitely, you're going to reach 1. Why? Because we're saying each time we're dividing by 2. So I have a half. And then the next time I'm adding the half of my half. The next time I'm adding the half of this half. So I'll continue doing this. If I continue doing it till infinity, I'll reach 1. That means we prove this is going to be less or equal than 1. Okay, so just keep this math rule in your head before we move here. So what is the idea here, guys? We have levels. What is the height here? Height is 3, correct? So guys, focus with me a bit. The height is 3. What do we mean by this? Why do I need 3 swaps here? Because if I'm swapping here, what is the maximum swap I can have? 1, 2, 3. If I'm at this level, what is the maximum swaps I can do? 1, 2. If I'm here, there's nothing to swap with. So what is the conclusion I can get from here? Is that for each level I, there is h minus I swaps. So that's the conclusion that we can make. So keep this in mind. For each level, I have h minus I swaps. So in this case here, let's say I have 3 levels. What will happen? At level I, the number of swaps is less or equal than h minus I. At level I, there are how many nodes? 2 to the power of I. We know all of this from last session. But it's not equal. Why it's not equal? Because at the last level, it's complete binary tree. So it's going to be at most 2 to the power of I. So what can we conclude in this case? That the total number of swaps, I need to add them. Each time, it's costing me h minus I swaps, right? So this one cost me h minus 1 swap. This one cost me h minus minus 1 swaps. So for this level, how many swaps? H minus 1 times 4. Correct? So times the number of the nodes. So the idea here is the number of swaps times the number of nodes for each level. So I have to do the summation. Now I want to get this to be very similar to the formula that I gave you in math, like summation of 2 to the power of minus j. We want to try to make it similar so we can conclude with the other thing. So what's going to happen? You can take a look at this at home slowly, but the idea here is what? I have this, correct? I just replace h minus 1 by j just to make my calculation easier. That's the only reason I'm doing this. So in this case, what do I have? J 2 to the power of h minus j. Okay, instead of I also replace it with h minus j. I can just take 2 to the power of h outside. I'll end up with 2 to the power of h of j 2 to the power of minus j. Now this, what did we say? We have this rule for it. But let's understand why do I have the 2, 3, and 4 here? Because I still have the j. So for j equals 0, I don't have it. For j equal 1, I'll have 1 times 2 to the power of minus j, which is 1 times 2 to the power of minus 1. That's 1/2. The next one, I'll have to what? J is equal to 2 times 2 to the power of minus 2, correct? I'll have this. Now, how can I get from this to this? How many 1/2 I have? Only 1. So I used it in the first time. How many 1/4 do I have? I have 2 1/4. What is this? This is 2 times 1/4. That means I have 2 1/4. How many 1/8 I have? 3. For the first line, I can say 1 plus plus plus, which is technically less or equal than 1. I already proved it. My next run, I'll have the same thing without the 1. Why? Because I don't have more than 1. Then the third one, the same thing. I have 3 here, but I only have 2. What's going to happen in this case? I'll have 1 plus half plus 4. We'll end up with 2. So this is going to be less or equal than 2. Again, guys, at home, you can look at it very slowly. But the idea here, I proved now that this will end up with less or equal than 2. Now, if this here is less or equal than 2, I still have the 2h. Why is my 2 to the power of h and yes?
Because h is log n.
Very good. So because of this, technically, if you look here, I know that because this is a complete binary tree, we have 2 to the power of h plus 1, if you remember. And why do, like you remember from in the last session, we actually did it all the math for it. So if you continue with the logic, I have h is log of n, and you just do the math, you're going to end up with 2n here. Please take a look at it slowly, step by step at home. Check the previous lecture. If you still have questions about the math and you're just curious about the math, we can always discuss it in the next lecture. So we will end up with O of n. Why? Because 2n is going to be O of n. So we actually proved that it's O of n. Okay, very good. Now, the implementing, very quickly, we're going to talk a bit about the implementation, and then we're going to go to a WOOC lab. We will do the sorting part next time. We said to implement it by an array, guys, it's very easy because you can use 2i plus 1, 2i plus 2. Guys, why we're using 2i plus 1, not 2i?
Shut up.
I've been giving the example for 2i. Look.
James is an expert.
I said, look, sir. Yeah.
2i plus 1, it's when you start by 0.
Okay, very good. So technically, if I'm starting the index here by 1, it's 2i. If I'm starting the index by 0, 2i. Okay, so technically, again, this is just implementing. So these slides are the same as we explained last time, the same exact slides. I'm not going to go through them. You know how we're going to be implementing them. Also, you can do the thing with a linked binary tree, and the sorting, we'll leave it for next time. So let's do the WOOC lab quickly. Okay, let's do the WOOC lab. I have 5 minutes only, so let's do it. You see, now it's starting to be more fun, right?
Just wrong, worst day possible.
Then we're going to do heap sort, AVL, 240. Everything is going to be actually very interesting from now on.
Friday, but I haven't gone yet.
Up to before the reading week. We're going to cover AVL for sure.
Like,
Yes.
how to you. Even my assignment.
Absolutely. No, you don't ask this stuff.
It depends on the question, but usually sometimes we ask actually constructed. Or we give you a multiple choice and you construct it with the paper and you give me the answer. Anyway, okay, guys, so I think everyone is in. Let's start, guys.
So it's like,
Big O of method insert of a heap. When I'm inserting using a heap, what is the method? Quickly. Log of n, of course. The array that represents a min heap is always sorted. The array that represents a min heap is always sorted. Because the root is the minimum key, of course. Of course, it's false, because that's the whole idea. If I have a sorted array, then that means that's nothing. I'm still using an ordered sequence. Can I do a heap sort in place? We didn't cover heap sort. Method, remove min and remove max. Actually, you shouldn't know this because we didn't cover it, but technically it's always going to return it, because the idea here is that we said we remove min is the same as the ADT that we used. Do you remember the ADT that we used last time? Guys, this is important. Why we're returning here? Why didn't I have to explain it again for you? Because we already designed the priority queue ADT last time. We're just using a different implementation, but the remove min still does the same thing. If we're using a ordered sequence or if we're using a heap. In this code below, which method is being performed first? The insert or the remove? This is the coding. So that's, you asked me, for example, would be in the exams, would we have programming questions? So technically, we're not going to ask you to write a program, but if you get something like this, you need to be able to understand what's happening, right? So which method is performed first, the remove min or the insert? Definitely the remove min, because the remove min is inside the bracket. So you have to solve, you have to remove before you insert. If I'm constructing a min heap with bottom-up heap construction, after dividing it to mini heaps, I will perform what on the min heaps? Down heap or up heap? We said bottom-up heap construction, we're treating each 3 nodes as a mini heap. What are we doing? Down heap or up heap?
Circuits.
50-50. Who says down heap and why? I need to new faces. Down heap and why? Quickly. Yes.
Up heap, you might have to do it twice.
Exactly. We just explained it, guys. We explained it like 5 minutes ago. We said up heap, we're going from down to up. That means it may take you 2 tries to get what you want. But with the down heap, it's only 1 swap, and for sure you're going to do it. So technically, it's down heap. We're going to cover it again. If I'm constructing a max heap with bottom-up heap construction, after dividing it to min heaps, I will perform what? Now I'm using max heap, not min heap. Would I do down heap or up heap? Answer, guys, without talking. It's a trick question. You still didn't get the concept. So next time I have to go through the down heap and up heap again. Guys, next time I'll go through this because I don't think it clicked in your mind. This, don't worry, we're going to go through it again. Okay? And that's it.
Yeah.